Discover advanced plate bending technology and heavy steel manufacturing that shape powerful structures with precision, strength, and engineering innovation for modern industry. The plate bending process begins with the preparation and positioning of a large steel plate that will be formed into the required curved shape. Due to its considerable size, thickness, and weight, the steel plate cannot be handled manually. Instead, an overhead crane installed in the workshop is used to lift the plate safely from the storage area. Steel lifting slings or chains are securely attached to the plate, ensuring balanced lifting and preventing unwanted movement during hoisting. Once the crane operator lifts the steel plate, workers standing on the shop floor carefully guide it using hand signals and guiding tools. Their role is essential to keep the plate stable and properly aligned while it is suspended in the air. The plate is slowly moved toward the plate bending machine, maintaining a controlled speed to ensure safety and accuracy. Throughout this step, clear communication between the crane operator and ground workers is maintained to avoid misalignment or sudden movements. As the steel plate approaches the machine, workers gradually lower it into position. The plate bending machine typically consists of multiple heavy-duty rollers designed to handle thick steel plates, such as 56 mm plates shown in the process. The plate is carefully placed onto the lower rollers of the machine. Workers make fine adjustments to ensure the plate is centered and aligned correctly with the bending axis. Proper alignment at this stage is critical, as it directly affects the uniformity and accuracy of the final bend. After positioning, the machine operator begins the bending operation by adjusting the upper roller. This roller applies downward pressure onto the steel plate, while the lower rollers rotate, pulling the plate through the machine. As the plate moves forward, it is gradually bent into a curved form. Instead of bending the plate all at once, the machine applies pressure progressively. This controlled approach helps prevent cracking, surface damage, or uneven deformation, especially when working with thick steel. During the bending process, the steel plate passes through the rollers multiple times. After each pass, the operator slightly increases the pressure or adjusts the roller position to achieve the desired curvature. Workers closely monitor the plate's shape, checking the bend radius and overall geometry. If necessary, the plate is repositioned or rotated to ensure consistent bending across its entire length. In some cases, partial bending is performed first, followed by additional passes through the machine. This step-by-step method allows greater precision and reduces internal stress within the metal. The rotation of the rollers and the gradual application of force ensure that the plate bends smoothly without sudden deformation. Throughout the process, the machine operates at a controlled speed to maintain accuracy and safety. As the plate reaches the required curvature, the operator reduces the pressure on the rollers. The machine slows down, and the plate is carefully guided out of the bending area. Workers assist in supporting the plate as it exits the rollers, ensuring it does not drop or shift unexpectedly. The curved steel plate is then inspected visually and, if required, measured to confirm that it meets the specified bending radius and dimensional requirements. If the curvature is not yet perfect, the plate may be fed back into the bending machine for further adjustment. Minor corrections are made by fine-tuning the roller pressure and repeating the bending cycle. This iterative process continues until the desired shape is achieved with high accuracy. Once the bending operation is complete, the overhead crane is used again to lift the finished curved plate from the machine. Workers attach the lifting equipment and guide the plate as it is raised. The plate is then moved to a designated area for further processing, such as welding, assembly, or surface treatment. Overall, the plate bending process relies on the combination of heavy machinery, precise control, and skilled human coordination. The use of an overhead crane ensures safe handling of large steel plates, while the plate bending machine provides the controlled force needed to form thick metal accurately. Each step, from lifting and positioning to gradual bending and final inspection, plays a crucial role in producing high-quality curved steel components for industrial applications. The hydraulic plate rolling machine MCB 4-roll series is designed for precise and efficient bending of heavy steel plates. This advanced machine can roll plates with thicknesses ranging from 10 mm to 200 mm and widths from 2 up to 6 meters. Thanks to its 4-roll configuration, the bending process is highly accurate and stable. The system is user-friendly and fast, with a plate advancement speed of up to 6 meters per minute. Overall, it represents one of the best plate rolling solutions available on the market today. The sheet metal bending process begins with carefully placing a long steel plate into a 3-roller sheet bending machine. The steel plate is aligned to ensure uniform curvature along its length before the machine is started. As the upper and lower rollers rotate, the steel plate is gradually pulled into the machine and subjected to controlled pressure. The central roller applies downward force, while the side rollers guide and support the material, causing the flat plate to bend smoothly. With each bend, the curvature increases until the desired cylindrical shape is achieved. Throughout the process, the operator monitors alignment and bending radius to ensure accuracy, producing a precisely shaped cylindrical metal shell ready for further processing or assembly. The steel plate bending process begins with preparing a flat steel sheet of the required thickness and dimensions. Before bending starts, the plate is carefully aligned and fed into the 3-roll bending machine. This machine consists of 3 cylindrical rollers arranged in a triangular configuration, allowing the steel plate to be gradually formed into a curved shape. Once the steel plate is positioned between the rollers, the bending operation begins. The lower rollers support and drive the plate forward, while the upper roller applies controlled downward pressure. As the rollers rotate, the steel plate moves steadily through the machine. The applied force causes the plate to bend progressively rather than all at once, which helps maintain material integrity and prevents cracking or deformation. During the process, the operator adjusts the position and pressure of the upper roller to control the bending radius. By making multiple passes through the rollers, the plate is gradually formed into the desired cylindrical or curved shape. This step-by-step bending method ensures high accuracy and uniform curvature along the entire length of the steel plate. As the bending continues, the steel plate conforms closely to the target diameter, such as a 400 mm pipe form. The machine's synchronized roller movement guarantees smooth bending and consistent results. Once the required curvature is achieved, the bending operation is stopped, and the formed steel plate is carefully removed from the machine. Finally, the bent steel plate is inspected to ensure it meets dimensional and curvature requirements. This 3-roll bending process is widely used due to its efficiency, precision, and ability to handle thick steel plates in industrial fabrication. The Manguzzi/Fisher Plus Ruckle Double Knife Guillotine with Glue application, Model 45-3400's Pultra, is a high-performance cutting solution designed for precision paper and board processing. This double guillotine system integrates accurate cutting with an inline glue application, ensuring clean edges and efficient downstream handling. The machine offers a maximum cutting length of 3,400 mm and a minimum length of 1,050 mm in the grain direction, making it suitable for large format materials. In the cross-grain direction, it provides continuous cutting widths from 65 to 450 mm and discontinuous widths up to 800 mm. With a productivity of approximately 2.5 bundles per minute in continuous mode and 1.5 bundles per minute in discontinuous mode, the Pultra model combines speed, accuracy, and reliability for industrial finishing operations. The machining process begins with positioning a 30-ton heavy component securely on the horizontal boring machine table. Due to its massive weight, precise alignment and rigid clamping are essential. The boring machine then performs accurate drilling and internal machining operations, ensuring tight dimensional tolerances. Controlled cutting speeds and steady tool movement allow the machine to remove material efficiently, while maintaining stability, precision, and surface quality throughout the entire process. The RMT Pipe Spool Master 32 is a high-performance pipe machining lathe specifically designed for fast and accurate end preparation of large diameter pipes. Its primary function is to apply precision bevels, face pipe ends, and perform threading operations when required. What makes the Pipe Spool Master 32 stand out is its impressive capacity range, allowing it to machine pipes from 6 inches up to 32 inches in diameter. In addition to this model, The series includes machines capable of handling pipes as small as 1 inch and as large as 144 inches, offering exceptional flexibility for a wide range of applications. This machine is capable of producing both standard and complex bevel profiles. It can perform internal seat dimensions, counter-boring, precise landings, and concentric bevels, all with a single tool equipped with dual cutting heads. One of its major advantages is speed. For example, a 30-inch stainless steel pipe with a 1.5-inch wall thickness can receive a complex bevel in under 15 minutes, significantly reducing processing time compared to conventional equipment. A key feature of the Pipe Spool Master 32 is its ability to find the true center of a pipe, even when the pipe is out of round. Adjustable pipe supports and a movable cutting head allow precise alignment, ensuring accurate bevel geometry and consistent quality. The machine also features a conversational control system, making programming simple by entering dimensions, angles, and seat depths directly. Material handling is enhanced by an integrated up and down conveyor system with rollers and a lazy Susan, allowing easy pipe positioning and 180-degree rotation without cranes or forklifts. Overall, the Pipe Spool Master 32 delivers speed, precision, and versatility for demanding pipe fabrication environments. In the spiral pipe manufacturing process, welding is the most critical operation to ensure the structural strength, pressure resistance, and long-term durability of the pipe. Once the steel strip has been formed into a spiral shape and the edges are precisely aligned, the welding process begins with external welding. First, the outer seam of the spiral pipe is welded using automatic submerged arc welding technology. A continuous welding wire is fed automatically into the welding head, while granular flux is deposited over the weld zone. When the electric arc is generated beneath the flux layer, the arc melts both the wire and the base metal edges, forming a strong and uniform weld bead. The flux completely covers the arc, preventing atmospheric contamination, reducing spatter, and ensuring deep penetration. The welding machine moves steadily along the spiral seam, maintaining constant voltage, current, and travel speed to achieve consistent weld quality along the entire pipe length. After the external weld is completed and sufficiently cooled, the process continues with internal welding. The pipe is positioned so that an internal submerged arc welding system can access the inner spiral seam. Similar to the external operation, an automatic wire feeding mechanism supplies the welding wire, while flux is applied to shield the arc. The internal saw process reinforces the joint by fully penetrating the seam from the inside, ensuring complete fusion through the pipe wall thickness. This step significantly increases the mechanical strength of the weld and eliminates any potential internal defects left after external welding. Throughout both external and internal welding stages, parameters such as wire feed rate, welding current, arc voltage, and travel speed are continuously monitored and controlled automatically. This guarantees uniform weld geometry, high bonding strength, and excellent metallurgical properties. The combined external and internal submerged arc welding process results in a robust, continuous spiral weld seam capable of withstanding high pressure and demanding service conditions. Steel strip coils are first placed on the uncoiler, where the material is smoothly unwound and guided into the production line. As the strip moves forward, it passes through a leveling unit that removes residual stresses and corrects any curvature, ensuring a flat and uniform input for precise forming. The leveled strip then enters the forming section, where a series of sequential roller stands gradually bend the flat strip into a round tubular shape. Once the edges of the strip are properly aligned, the tube passes through the high-frequency welding station. Here, concentrated electrical energy heats the edges, and pressure rollers forge them together to create a continuous, strong longitudinal weld. Immediately after welding, excess weld bead on the outer surface is trimmed off to achieve a clean and smooth finish. The welded round tube then moves into the sizing and reshaping section. In this stage, specially designed rollers progressively transform the round tube into a square profile. Each stand carefully controls the deformation, forming sharp and consistent corners, while maintaining uniform wall thickness and dimensional accuracy. Fine adjustment of the rollers ensures that the square tube meets strict tolerance requirements. After shaping, the square tube is guided through a cooling system, where water or air cooling stabilizes the material and relieves heat generated during welding and forming. The cooled tube then passes through straightening rollers that correct any minor distortions and improve overall alignment. Finally, the finished square tube reaches the cutting unit, where it is cut to predetermined lengths using a flying saw or cold cutting system, synchronized with the line speed. The cut profiles are then collected on the runout table, inspected for surface quality and dimensional accuracy, and prepared for packaging or further processing. The entire line operates continuously, combining efficiency, precision, and high production output. The steel pipe production process on the TPC-1 mill at Volsky Tube Plant begins with the arrival and preparation of high-quality steel billets. These billets are first inspected and preheated in a furnace to reach the proper temperature for forging. The controlled heating ensures the steel becomes sufficiently plastic, enabling it to be easily formed without cracking. Once the billets reach the desired temperature, they are fed into the TPC-1 rolling mill. This advanced mill operates on a continuous rolling-on mandrel principle, where the heated billet is pierced to form a hollow shell. The mandrel inside the rolling stand shapes the internal diameter, while the external rollers compress the shell, gradually reducing wall thickness and expanding diameter to meet the specified dimensions. During rolling, sensors and automatic controls constantly monitor key parameters such as temperature, speed, and dimensional accuracy. This ensures that each length of pipe adheres strictly to quality standards. Operators can adjust settings in real time to maintain consistency and prevent defects. After the final rolling pass, the newly formed pipes exit the mill and are cooled on a controlled cooling bed. This stage solidifies the steel's microstructure, enhancing strength and toughness. Once cooled, the pipes are straightened and cut to the required lengths. The final stages include surface inspection, ultrasonic testing, and measurement checks. Any pipes that do not meet the criteria are set aside for rework or recycling. Approved pipes are then marked, bundled, and prepared for shipping. Overall, the TPC-1 production line combines precision engineering, automated control, and rigorous quality assurance to manufacture durable, high-performance steel pipes for industrial use. The fully automated 4-roll plate rolling machine developed by FACCIN represents an advanced technological solution designed specifically for the efficient manufacturing of wind tower sections. This modern system is engineered to handle heavy steel plates with high precision, speed, and reliability, ensuring superior productivity in large-scale industrial environments. The process begins with a motorized feeding table equipped with an automatic alignment system. Steel plates are loaded onto the table and positioned accurately without the need for manual adjustment. Once in place, the CNC-controlled feeding mechanism guides the plate smoothly into the rolling unit. The automated plate alignment function ensures that the material enters the machine perfectly straight, eliminating positioning errors and reducing setup time. A key feature of the machine is its high plate pinching power, which firmly grips the material between the rolls. This strong clamping capability allows for powerful and accurate pre-bending with an extremely small flat end section. As a result, the amount of unformed material at the plate edges is minimized, improving the quality of the final cylindrical section. The precise plate bending system guarantees uniform curvature along the entire length of the workpiece. Thanks to its intelligent control system, the machine achieves precise bending with less need for re-rolling. Secure side supports stabilize the plate throughout the operation, preventing deformation and ensuring consistent results, even with large and heavy components. The rolling process is optimized through simultaneous movements of multiple machine axes, significantly reducing overall cycle time. Productivity is further enhanced by the high operational speed, with a maximum rolling rate of up to 7 meters per minute. The integrated automation system allows most operations to be performed with very limited involvement from the operator. This not only increases efficiency, but also improves workplace safety and reduces human error. Before tack welding, the machine performs precise plate edge alignment, guaranteeing perfect joint preparation. While tack welding is carried out directly on the machine, the system simultaneously prepares the next plate for processing. This parallel workflow greatly accelerates production and minimizes downtime between operations. Once the rolling and welding stages are completed, the finished cylindrical shell is automatically unloaded from the machine. The entire sequence from loading to unloading is carefully coordinated to ensure smooth and continuous manufacturing. In conclusion, the FACCIN fully automated 4-roll plate rolling machine provides a comprehensive and highly efficient solution for producing wind tower sections. Its advanced automation, accuracy, and high speed enable manufacturers to achieve faster production, superior quality, and reduced labor requirements, making it an essential piece of equipment in the renewable energy industry. The manufacturing process of wind turbine towers begins with large steel plates delivered to the workshop. The plates are transported to the cutting and grinding table, where advanced cutting machines shape them into the required dimensions. After cutting, the edges are carefully ground to ensure clean and accurate surfaces for further operations. The prepared plates are then moved to the rolling stage. Powerful plate rolling machines gradually bend each steel sheet into a precise cylindrical form according to the design specifications. Once the plate has been rolled, skilled welders align the two ends and weld them together to create a closed tower section. When the longitudinal welding is finished, the inner weld seam is thoroughly inspected. Technicians grind and smooth the joint to remove any irregularities and to guarantee structural quality. In the next step, the large cylindrical sections are placed on welding rotators, also known as turning rolls. These rotating supports allow the components to turn while welding machines perform circumferential welds on the ends of the sections. This operation joins parts and prepares them for assembly. After all welding activities are completed, each tower segment undergoes surface preparation. The exterior is cleaned and sprayed with protective paint coatings to resist corrosion. Finally, detailed inspections verify dimensions, weld integrity, and coating standards before the tower sections are approved for delivery. A transition piece is a crucial structural element used in offshore wind and energy projects. The process begins with manufacturing secondary steel components, such as platforms, boat landings, ladders, and other functional appurtenances. These specialized parts are produced in series with extreme accuracy to meet strict engineering requirements. After fabrication, the components and the large tubular structure are transported to the Hoken yard for final assembly. Each part is precisely positioned and welded by qualified welders, while every weld is inspected and approved by external specialists. A multi-layer protective coating system is applied in accordance with rigorous procedures to ensure long-term resistance in the demanding offshore environment. Once coating is completed, the tubular structure is lifted, upended, and a large platform is installed. Finally, electrical and technical equipment is fitted, and the transition piece is fully prepared for offshore installation. The manufacturing process of the steel tower sections begins with large flat steel plates that are delivered to the production line. Each plate is positioned precisely and fed into a powerful bending machine. The rollers of the machine gradually curve the plate until it forms a circular shape. Once the required diameter is achieved, the two edges of the curved plate are aligned carefully. These edges are then welded together to create a complete cylindrical shell. After the initial welding stage, the newly formed tube is transported out of the bending area to continue through the production sequence. At the next station, specialized equipment is used to clean and prepare the surface of the tube ends. This cleaning operation removes impurities and ensures that the edges are perfectly smooth and ready for further joining. Proper surface preparation is essential to guarantee high-quality welds in the later stages. Individual tube sections are then moved by an overhead gantry crane. The crane lifts each heavy segment and places it accurately into position beside the next section. Workers align the pieces with great care to maintain the correct dimensions of the future wind tower. Once aligned, skilled welders use advanced welding machines to carry out precise circumferential welds. These welds join the separate steel tubes into longer and stronger sections. The process is repeated until the full length of the tower tube is completed. When all welding operations have been finished, the weld seams are carefully inspected. Technicians grind and smooth the welded joints to remove any irregularities and to create a uniform surface along the entire structure. This finishing step improves both the strength and the appearance of the product. After grinding, the steel tower section moves to the final treatment area, where it undergoes protective coating. In the last stage of production, the completed tower tubes are spray painted with high-quality industrial coatings. The paint protects the steel from corrosion and harsh environmental conditions. Once the coating has dried and final quality checks have been carried out, the finished sections are prepared for transportation. They are carefully loaded and shipped to their destination, ready for installation as part of a complete wind turbine tower. Production begins with high-quality alloy steel bars delivered to the plant. The bars are inspected and cut into short billets of precise weight. Each billet is heated in a continuous furnace to the required forging temperature. The hot pieces are transferred to automated forging presses, where they are formed into spherical shapes. After initial shaping, the balls enter rolling mills that refine the roundness and achieve accurate dimensions. The forged balls are then sent to a controlled quenching line for rapid cooling to obtain high hardness. Tempering furnaces reduce internal stress and improve toughness. Finally, the finished grinding balls undergo surface cleaning, hardness testing, and dimensional quality inspection before packaging for safe delivery to customers worldwide with full traceability records. The production and assembly process of steel structures begins with the preparation of raw steel materials. Large steel plates and profiles are first positioned on automated cutting tables, where precise dimensions are marked according to technical drawings. Using advanced plasma and oxy-fuel cutting machines, the steel components are cut into the required shapes and sizes. This cutting stage ensures that every part matches the exact specifications needed for further processing. After cutting, the individual pieces are transferred to the welding area. Skilled welders and robotic welding systems join the components together to form larger structural elements such as beams, columns, and frames. The welding operations are carried out in several stages to guarantee strength and accuracy. Tack welding is performed first to hold the parts in position, followed by full seam welding to create permanent connections. This stage requires strict control to maintain alignment and structural integrity. Once welding is completed, the welded joints and surfaces undergo grinding. Grinding machines and handheld tools are used to remove excess material, smooth rough edges, and prepare the surfaces for the next welding phase. In many cases, additional welding is required after grinding to reinforce critical areas or to attach secondary components. This alternating sequence of welding and grinding continues until the structural elements reach the required quality and finish. Following fabrication, each component passes through a detailed inspection process. Quality control specialists carefully examine weld seams, dimensions, and surface conditions. Non-destructive testing methods are applied when necessary to verify the strength and reliability of the joints. Only elements that fully comply with technical standards are approved for the next stage. Approved structures are then moved to the painting section. Here, the steel surfaces are cleaned and treated to remove dust and impurities. Protective primer layers are applied first, followed by final coats of industrial paint. This coating process protects the steel from corrosion and ensures long-term durability in various environmental conditions. The final stage is on-site assembly. Finished and painted steel components are transported to the construction location. Cranes and lifting equipment are used to position the elements accurately according to the project layout. Workers connect beams, columns, and other structural parts using bolted and welded joints. Step by step, the separate pieces are assembled into complete frameworks, forming the skeleton of industrial buildings and facilities. Through this carefully organized sequence of cutting, welding, grinding, inspection, painting, and assembly, high-quality steel structures are efficiently manufactured and erected to meet modern construction demands.